Good, okay. Now one of the problems is that, in fact, the parameter for which value for this guy is maximized, could be very different or could have very low probability under your prior. So if you just make a plot of your prior, it could be something very informative, like the uniform distribution between 0 and 1, okay? But if you have, let's say, 1 million coin tosses and 600,000 of them are 1s and the rest are 0s, then basically your likelihood function will be like this. Okay? 6. So it will be almost like a delta function. So what will happen is that whenever you sample, according to the distribution, most of the time you end up getting a point here where it's 0. Or almost 0. So you get a very, very bad estimate of its likelihood. Okay? So what is the right way to do it? Well, you should have some other distribution you sample from which maybe is closer to this likelihood somehow. Yeah? So maybe it's like this. If you had a way of generating a distribution like that, then it would be nice. Why? Well, let's see. So let's look at this integral again. And this is just the probability of the data under the belief C. Now we're going to divide and multiply by the same distribution, psi. It's simply called the proposal distribution. It's different from our belief, but some other distribution that we hope is more efficient in terms of estimating the value of this integral. Okay? We hope. It might not be true. Now if you just move this around, then the integral kind of becomes like this, right? So now here we want to estimate basically the expected value of p by randomly sampling from C. Oh, I have an error there. I'm so silly, sorry. I have to fix this error, because it's very bad. I put this thing there, which shouldn't be there. Totally make mistakes. Okay. Now the rest should be correct. Yeah, that's correct. Okay, yeah. So basically, yeah, this thing disappears now, right? Oops. Not the whole thing, but something disappears. Okay. Yeah. So this thing disappears now because we just sampled from it. And here again, you see that what we have is we are estimating the expectation of this and the distribution of psi. Yeah. So psi goes away, and we just have the sum of the probabilities of the data multiplied by this ratio. Okay? And this is the probability of this parameter value under one relative to the another. Okay? So that's all there is there. And this is called importance sampling because you basically increasing the importance of some of the samples than the others by this ratio. Okay? That's the idea, at least. Now, I said there's a problem with the scaling factor. It can be large, but so you can reduce this variance a little bit, but actually this might also have problems with you having too high variance. So this might be very low in some places, making this whole thing very high. So ideally, this should be very close to this value here, so that I can cancel out.
You cancel your mouse, so when you say this, it's
Okay, you were seeing mouse. Now you're seeing mouse.
yeah.
So these things should kind of cancel out. So this should be higher when this is higher. Yeah, if it's low when this is high, then this is very bad. Yeah. So if you calculate the distribution in a nice way, then you have a better performance than just doing it like this. Now, just doing pure important sampling is not, again, very good because we don't really know how to select this. Right? So there are methods called Markov chain Monte Carlo, which we're not going to talk about at all. But the basic idea is that you can add distribution in some way over time so as to better match your the actual thing you want to approximate. These run into other problems. It can take a long time to converge for them, and it's hard to prove anything about how fast they converge. Here you have some known bounds, like this one, but it's hard to say how big this quantity is, and this kind of changes the constant in the bounds. Okay, but these are the two basic ways you can do it. There's another way called variational inference. We're not going to mention that. Beyond saying the name, but you will hear about it probably. Have you heard about variational inference? No. Okay. So it's basically a bound on these probabilities. Okay. What I would like to go today through before we break is the idea of sequential updating of this marginal likelihood. So calculating this is hard, but for some models you can do another trick. Okay. And let's do that again. So the marginal likelihood is basically the probability of the data under our belief. Yeah, so normally we integrate over all possible parameter values. Okay, but the data we have is not just one complicated data object, it's a sequence of data points, right? So the idea here is that the probability of all the data, you can just break it down like this. This is just standard joint distribution notation where the conditional and the marginal of this one makes a joint distribution of all the variables, right? Yeah? Good. That's the important thing here, right? So you can rewrite this now. You can just do this for all of these, so x1, x2, x3, x4. And you will have this term here now. Probability of xt given x1 until xt minus 1. You can rewrite this again, but we don't need to do that, but just to explain what this is. So this term basically here is the probability of that data point t given your posterior at time t. Yeah. So you can just break it up. So that means that if you have an easy way of calculating the posterior at time t, then it's easy basically to calculate what this is at every time step. Yeah. And we have an example, we have the Bethe-Bernoulli example, right? In the Bethe-Bernoulli example, the probability of x equal 1 given all the previous data is basically this ratio of posterior parameters. It's essentially the number of times x was 1 and the number of times x was 0, plus a constant for alpha and for beta, which is the prior parameters. Yeah. So if you remember, initially you have a uniform belief, right? Then you have an alpha 0 equal 1, theta 0 equal 1. If you observe x equal 1, then this becomes 2, and in this curve becomes like that. Okay. This one doesn't change, this one changes. So this is what this equation they represent. Every time you see 1, you increase the alpha. Every time you see a 0, you increase the beta. So then, to calculate the product of these things, but calculating the product of these things, you just get the likelihood. So it's quite simple. Yeah. So we could do that, right? Just to calculate the likelihood for our specific models. Yeah. And what are the specific models we have those two models, right? Now, we did say that we didn't care so much. Well, we only care about this link here, right? In some sense, whether this link exists or not, right? So, for example, because the data is split into parts, right? Maybe you can do a tricky thing, but let us focus on this link here. So let's say we have, let's ignore this x2, okay? And say we have data from x1 and x3 only, and either these are independent or there is a link between them. Yeah. Okay. So then we basically have for x1, it's the same. In the sense we can, it's the same model for both cases because they both say x1 is independent. So I have to ignore the data about x1 by itself. But let's see, think about the data for x3 given x1. So in one model we say, well, x3 should depend on x1. For the other model we say it does depend on x1. So in one model we have one parameter, and the other we have two parameters, depending on the value of x1 or x2. So how can we do inference with this? Well, let's see. Okay, let's move this here. So we had that's okay, I guess. Maybe it's not super readable, I don't know. That's better. Okay. Okay, so we have this data, right? And we can generate data in many different ways. And in this particular case, x, z depends on x, y depends on x, and let's say a also depends on x, right? Okay. Somewhere should be, oh, there it is. So now we are going to plot, to print and plot some things. Okay. So here we print out the deviation, okay, between the distribution of y given z equal 1 and the distribution of y given z equal minus 1. Of a given z equal 1 and z equal minus 1, as well as the marginal for the model which says they are independent. Okay, for the cases where y equal 1 and y equal minus 1. So we see that for those three models, the distributions are quite different. So there's a difference between z equal 1 and z is minus 1. Yeah. So that tells us that probably these models are not in agreement, right? So because they're not in agreement, there's not independence. Yeah. And this is agrees with this deviation here. Okay, this is quite large. So if it's 0, then it's probably there's independence. Now if we change the amount of data, okay, let's put 100, right? It should be similar. Yeah, you see, now we just by chance we got a small deviation here, right, for y equal 1. But we do see something similar here, right? But we're not really sure. So the fact is that even though there seems to be an agreement, the fact that these distributions are kind of wide means that we're not really sure whether they're the same or not. Okay. So if they are all very sharp and they were at the same point, then we would know that the distributions are, the values of this parameter are the same. So here we say under the marginal model, it could be anywhere between here and here, and under z equal 1, it could be anywhere between here and here, and under z equal minus 1, it could be anywhere between here and there. So it's quite wide where it could be, right? And these are all independent things. If we increase the amount of data, on the other hand, we will see much sharper plots. So now it's always that they're different, right? So if you do the product of these things, basically, then the products are 0, almost. Yeah. So there's no overlap at all. And here you have just this number that tells you how much they deviate. But here you're also pretty sure that they are really different distributions at this point. Now, if you see that the data is, you make the data independent, so let's make A just random. Yeah. Then we should see now that the distributions are the same, right? Or more or less the same. Yeah. So they are the same, and the deviation itself is kind of small as well. Yeah. Now, of course, the problem is that if you have not so much data, it's hard to tell whether or not you have a large deviation because of randomness or not, right? So here you randomly get a large deviation, even though it's completely independent. But here, when you see at these curves, it's kind of obvious that you shouldn't really know. Yeah. There's not enough data to tell. Yeah. So now the question is, can we do the posterior calculation using this model, right? Okay. So, right. So, I will start it, okay, and you will finish it. Okay. Let's define a function. Okay, so you have a function, marginal, posterior, and you have data. It's either 0 or 1, let's say, or negative and positive, and you have your alpha parameter and your beta parameter. Okay. Now, how would this work? Okay, that's your prior alpha and prior beta, right? So let's say that n data has to be length of data, right? Yeah. Now I'll just make it with loops, right? Range n data. Now we said that the likelihood of each individual x has to be basically alpha divided by alpha plus beta. Okay. If x is positive and the other one otherwise, right? So okay, let's call this p. If x, okay, so total probability is 1. Now, if x is greater than 0, then total probability times p, right? Else total probability 1 minus p. Yeah, we agree? This is the probability of seeing x equal 1 under our marginal distribution, and this is the probability of seeing a 0 or not. Now, as we said in the formula, what we have to do is we have to increase alpha. We have to update our posterior at every time. So we increase alpha here and we increase beta here. Okay, that's it. Basically, that gives you the marginal posterior. Okay. There is actually a closed form solution that gives you exactly the same thing, because its beta distribution is very nice. So there's actually, but you can also implement it like this. Now, there's a problem with this, however. What do you think it might be? It's a computational problem. What is this p? It has range between 0 and 1, right? And you multiply them all together. So this becomes very, very small, very, very fast. So basically you get underflow. And your values, after some amount of data, your values don't make any sense, right? Okay, so what we usually do is the probability is equal to 0. Okay, and just remove this one and say log probability plus equal to, I guess, log p. It should be there. Okay. Okay, that's log probability. And then we just return the exponential of log probability. And every pair. Okay. So now we should be able to basically plug this in here for every one of these y and z values, okay, and say whether or not the model is independent or the independent one. Yeah. Because what you actually get is this gives you the probability, right, of all the data under the prior. Yeah.
In your last house, is first equals
yeah. Yeah, thank you. Yes, otherwise it would never work. Okay. Under the prior. Okay. So there's a, the other way of calculating this with integral is very stupid. In this case, it will never really work. Yeah. But sometimes it's your only choice. But here we have this very nice simple idea. You can use it. There's no problem. And now you can use this to calculate the posterior over two possible beta priors, the posterior ratio. Okay, so if you have alpha 1 and beta 1 and alpha 2 and beta 2 for two possible models, you basically have, remember, the probability of the model, right, is given the data is basically the probability of the data given the model, right? I'll just write this. Okay. So what do you have here? Yeah. So I have this one and the probability of the model divided by the other models, right? So I can just put them there. Okay. So you could calculate this. You have only two models. Just put an arbitrary prior. And this is not quite sufficient here, right? Because we have this case of independent beta for every possible value of z and I. So you kind of need to multiply all of them together to get the posterior of the model. Yeah, you might want to think about that a little bit, and we'll talk about it on the QA. So for that one, we must use the QA. Yeah. Yeah. We cannot do it online. You have to digest it a little bit. Okay. Okay, and I think that's it for explaining the models themselves up to now. So I would like to finish the stuff about fairness. Yeah. This one is not finished yet, so but I will finish it for you at some point. Okay. So we say that we can use this as a way to measure fairness, right, for a specific model. Okay. If we don't know the model, then we can use the Bayesian idea and that for a specific policy, we know how far away you are from being fair on average. Yeah. Another way that you can think about fairness was thinking about meritocratic decisions. So if I'm better than you, then I should get the job, right? For example. But the thing is that the quality of the individual is not visible to the employer, right? So it's hard to say, well, if somebody is better, then they should get better treatment. Well, you don't really know if they're better. So one way to think about it is to say that the employer has a subjective belief about the quality of individual, and he should select some individual with high probability when he's more likely to have better quality than the other. Yeah. But typically what you do, however, you say that if individual A is better than B in expectation, even if you don't know for sure, then you just hire person A, right? But we don't really want to do that because this kind of makes our decisions a little bit arbitrary. That's the idea. So The idea is that your decisions should be somehow smooth. So if it's hard to distinguish between two people, and even if someone appears slightly better, then maybe you should be a bit more random. So, okay, well, maybe I choose the other person. Okay, just to be sure that I don't discriminate. Maybe have a bias in your belief. I don't know. So the idea is normally you take this maximization, right? So this is perfectly meritocratic decision. You maximize expected utility under what you see about the individual, and there is some outcome, let's say your quality of the individual, and then the utility you get depends on your action. So you give the loan or you don't give the loan. Okay. Now, however, we would like to make this. There is some kind of work that relates this to smoothness of your decision. Say that, okay, if two people have data x or x prime, then you would like the distribution of your decisions to be similar when the data are similar. And this is something we looked at before. It's like the Lipschitz property of functions. We notice it in differential primes. So when databases are very close to each other, then the output of the algorithm is similar in distributional terms. Yeah. So it's the same idea exactly now for fairness. Say, well, if people are similar, then the probability of the same decision for both of them should be very close. Yeah. So there is a problem there, right? How do you actually define the similarity metric between two people? Yeah. In databases, it's pretty easy because, say, well, your data is there or your data is not there. That's the similarity between databases, and they are close. But for two people with some, I don't know, some resume and some things like that, it's hard to say, right? But what we care about, again, this is kind of an open question, what is the best metric, but you can try and learn from data. But what we really care about is mainly the quality of the individual. Yeah. So one idea, I'm not officially teaching this as course material, because kind of researchy, but I'll just discuss it. So one idea is basically that, okay, let's say you have some model, okay, for the quality of individuals. Okay, that's your model. It can be a Bayesian model or something, or a classifier trained with gradient descent or anything else. It doesn't really matter. Okay, so you have some model, and then you say, okay, the similarity, people are similar if their y distributions are similar. For example, you have p of y given x and minus p of y given x prime. Yeah, you can define this to be your distance metric between x and x prime. Okay? How much the distribution of y according to your model changes for different values of x and x prime. So two people might be very different in terms of what their x is, but if they result in the same quality distribution, then you should treat them equally. Yeah. So that's one idea. It's not the only idea out there, but in terms of these kind of meritocratic decisions, it kind of makes sense. Okay? But Now we mentioned before that we need to basically have some trade-off between fairness and utility. So that a typical way to do it in an optimization framework is to say that you put a different weight to utility and a different weight to fairness. Okay, and here let's call this the value of a particular policy for a particular parameter value for your model, because let's say there is a model with parameter theta describing the distributions between the relationship between the different variables, and the variable lambda, which is your trade-off between maximizing utility and maximizing privacy. So here is your utility, is your standard utility, let's say the amount of money you make in terms of the loans. And here your fairness valuation, other described in terms of deviation from conditional independence of a specific model, which can always measure, right, because it's for a specific model. You can always measure the deviation between the value, the distribution of a variable for different values of the input variables. So this one is always easy to measure. So you can think of it like, if you know the model, then you can think of maximizing this to solve the fairness problem. So if you just plug this into some optimizer, this gives you directly a solution to the fairness problem. Now the problem is that you never have enough data to actually know this parameter theta all the time. So the Bayesian decision theoretic idea here is very simple. It just says, well, just maximize this thing in expectation. So you have a belief about the parameter. Let's call it C. It can be based on some data. I don't specify the data there, but normally this is a distribution that was created from some data. And then you maximize the same thing now, but integrating over all possible values of theta. Yeah? That might be difficult, but it's not. Because in contrast to this Monte Carlo approximation that we talked about before, any gradient algorithm that is taken through some integral like this can be converted to a stochastic gradient algorithm by taking a sample from this distribution and then moving in the gradient direction for the sample with respect to this function here. I think we already saw this, right? A few weeks ago. Didn't we? I'm pretty sure we did. Okay, let's go to the So you want to maximize something, right? Okay, and then this maximizing thing is basically, in our particular case, integral g, x, and theta for some distribution over theta, right? So now one typical way to do maximization, or approximately, is to do gradient ascent. So that means you have to calculate the value, the gradient of x. Then that's basically the same thing as calculating the gradient of g for some value of theta and integrating. Now this is approximately the same as taking gx of theta n. Well, theta n is sampled from C. Yeah. So instead of calculating this integral and doing something very complicated, you sample theta, then you calculate the derivative of this function with respect to this specific theta that you chose, and then say x n plus 1 is equal to x n plus some step size and this is what is called stochastic gradient descent, because you replace the original gradient, which would have been something like this, yeah, take the derivative of f and then move in the direction of the gradient. Here you randomly select the g, a theta, and then you move in the direction of this randomly selected gradient. So what you do typically is think about like this. You have, let's say that these are, so that here's the maximum, yeah, and when you are here, then the gradient direction is there. If you are doing stochastic gradient descent, what happens is that you randomly select a direction, but these directions in expectation are equal to this direction here. So you're moving randomly, but in expectation you're moving always towards the center here. And in this particular case, this is called Bayesian quadrature, only because the stochastic gradient descent step is done with a distribution that is generated from a Bayesian probability. That's all. But it's basically stochastic gradient descent, and it's normally used in things like neural networks and stuff. But there, the data, this distribution is the empirical data distribution rather than the parameter distribution through some Bayesian posterior. But it's the same idea. Okay, I think